My name is Suresh, and in this video I'll be going over pretty much everything that we need to know about C2H2, which is the acetylene molecule in our grade 12 chemistry course. The first thing I'm going to be doing is building the Lewis structure. In order to do that, we need to determine how many electrons are in our electron bank. We can do that by taking a look at the electron configuration of carbon and of hydrogen. If this 2p2 was 2p6 in carbon, we would have a full octet, meaning that carbon has 4 valence electrons. Same thing here, if we had 1s2 instead of 1s1 in hydrogen, we would have a full octet, meaning that hydrogen has 1 valence electron. Before I continue and add electrons, we need to decide what is the central atom. This is kind of a special case since both elements are participating in equal numbers. There's actually no central atom. Therefore, we can determine right away that C2H2 is actually going to have a linear shape. So now let's continue and build the rest. We'll add 2 electrons between each element to start a chemical bond, and we'll add the rest of the 4 electrons out of 10 to any of the central atoms, in this case, either carbon, it doesn't really matter. So this hydrogen, this carbon, and this hydrogen are completely satisfied, but this carbon isn't. So what's going to happen is 2 of these electron pairs are going to move over here to form a triple bond between both carbons. So now we can get rid of those electrons and actually replace them with bonds so that we get a good idea of what it looks like. And this is our Lewis structure. But let's move on to something even cooler. Let's take a look at the 3D model that I built out of food. So I have a 4-sided potato shape as a triangular pyramid to represent carbon. It has 4 sides because it can take 4 bonds, which is why I chose this to be carbon. And I chose a semi-spherical carrot to represent hydrogen with only 1 flat side, since hydrogen can only accept 1 bond. The prominent angles in this 3D shape are 180 degrees this way as well as 180 degrees this way. One important thing that we need to talk about is polarity. C2H2 is actually non-polar. The reason for this is, number one, it's completely symmetrical, both horizontally and vertically. And it also has an electronegativity difference of 0.35, which is not past the threshold of 0.4 for it to be polar. So therefore, it is actually C2H2, the acetylene molecule, is actually non-polar. Now, let's talk about resonance structures. Is C2H2, does it have any resonance structures? Well, unfortunately, it actually doesn't. A resonance structure is basically a structure that has its electrons kind of rearranged. So the carbonate ion, CO3 2-, actually has 3 resonance structures. What really changes in between each of these valence structures is where the electrons are really arranged. So the oxygen that is double bonded to the carbon is changing in each of these. We can't do that in the acetylene molecule because carbon has to be triple bonded to carbon, it can't triple bond to hydrogen, and hydrogen can only have a single bond. Therefore, we can't rearrange any of the electrons, and therefore acetylene has no resonance structures. But what about isomers? Unfortunately, acetylene doesn't have any isomer as well. It doesn't have a structural isomer, a geometric isomer, or even an optical isomer. The reason acetylene doesn't have a structural isomer is because we can't really change the place of any of these atoms. In this case, oxygen is changing even though it keeps the same molecular formula in C2H2, and we can't do that here. Swapping these carbons keeps it the same, and swapping these hydrogens keeps it the same. We can't change carbon and hydrogen because hydrogen cannot accept a triple bond from another carbon, so therefore it has to stay the same. Acetylene can neither be geometric because, again, we can't move any of the atoms in acetylene. And finally, it can't be optical because even if we were to put it through a mirror, as we already discussed, acetylene is completely symmetrical. So what goes in, we will get exactly the same thing back. So acetylene has no isomer at all either. The last thing I'll be going over that's really chemistry heavy in this is a formal charge check. So right here, I have the Lewis structure. I've broken the bonds. I have 1 electron here, 1 here, 3 here, 3 here, 1 here, and 1 here. So when I group these up into each of their respective elements, I get 1, 4, 4, and 1. So hydrogen, as we discussed, has 1 valence electrons, 1 minus 1 is 0. Carbon, 4 minus 4 is 0. That applies everywhere, and so therefore, this is the most likely shape for C2H2. Now the last thing I'm going to talk about is what it's really used for. So acetylene in its pure form is actually pretty unstable and has pretty much always been handled as a solution. Prolonged exposure to heat or fire can rupture containers violently, and it's actually a widely used chemical building block and actually a fuel. It's also known as ethene, narcylene, or vinylene apart from acetylene. Thank you very much for watching my video, and I hope you learned a lot.